If the idea that a temperature spike 63 kilometers above the Earth can shut off the heat, lights, and water in your home simultaneously has you paying attention the way it has me, make sure to hit like and subscribe to Signal Watch so you don't miss a single update as this story develops. Drop a comment with where you're tuning in from, what time it is there, and this question. Has your city ever lost power and heat at the same time during a winter storm? Tell me what that was like. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. So thank you for having our back. Here's what this investigation is going to cover. A warming event in the stratosphere that moved faster than any model predicted, and what the European Center's ensemble runs actually showed in those final 72 hours before the vortex cracked in two. A grid compliance audit that found 62% of mandated winterization measures incomplete, buried in an appendix nobody read. The physics of wellhead freeze-off, and why natural gas infrastructure that survived Canadian winters fails at temperatures Texas sees every decade. And a water system failure cascade that doesn't just happen after the grid goes dark. It happens simultaneously, citywide, in hours, faster than any repair crew can move. Now, settle in and let's get into it. 63 kilometers above the Arctic, in a layer of atmosphere called the stratosphere, there is a wind. Not a wind like the one that rattles your windows or pushes weather systems across the map. This is something else entirely, a circumpolar river of air stretching pole to pole, spinning counterclockwise around the North Pole at speeds between 180 and 200 kilometers per hour, continuous and coherent, a planetary scale system that has been holding the Arctic cold in place above 60 degrees north latitude for as long as humans have had instruments sensitive enough to measure it. Scientists call it the polar vortex. The less precise but more accurate description is this. It is the lock on the freezer door. In a stable winter, the temperature at the core of that wind system, measured at the 10 hectopascal pressure level, roughly 31 kilometers up, hovers around minus 80 degrees Celsius. The wind itself is the product of a temperature gradient. The Arctic is cold, the mid-latitudes are warmer, and that difference in temperature creates a pressure gradient that sustains the rotation. The bigger the temperature difference, the stronger the lock. In January of 2024, that lock began to fail. The first signal wasn't dramatic. It never is. In early January, forecasters at NOAA's Climate Prediction Center began tracking an anomaly in what atmospheric scientists call the wave activity flux, the measure of large-scale atmospheric wave energy propagating upward from the troposphere into the stratosphere. When that upward wave flux gets large enough, it disturbs the stratospheric circulation. Disturbs it enough, and something extraordinary happens. The stratosphere warms. Rapidly. From the top down. Dr. Judah Cohen, who directs seasonal forecasting at Atmospheric and Environmental Research and has spent decades studying the relationship between stratospheric events and surface weather, has described the polar vortex as a system that appears stable right up until the moment it isn't. The wave flux anomalies that signal a coming disruption are detectable, measurable, and well understood. The question is always the same. Is this wave pulse strong enough to break the vortex, or will the system absorb it and recover? In January of 2024, the wave pulse was not absorbed. What followed was a sudden stratospheric warming event, defined by the World Meteorological Organization as the reversal of the zonal mean wind at 60 degrees north latitude and the 10 hectopascal pressure level from its normal westerly direction to easterly for a duration of at least 5 consecutive days. That definition sounds technical. What it means in plain terms is this. The wind that holds the Arctic cold over the pole reverses direction. The lock doesn't just weaken. It turns backwards. The operational definition used by NOAA's Amy Butler, whose 2017 climatology paper in Geophysical Research Letters remains the definitive reference on the subject, requires that reversal to be sustained. What the January 2024 event delivered was not merely sustained. The wind at 60 degrees north, 10 hectopascals, reversed from a westerly speed of plus 32 meters per second to an easterly speed of minus 18 meters per second in 72 hours. 50 meters per second of wind speed change in 3 days in a layer of atmosphere where normal variability is measured in single digits. At the same time, the temperature in the Canadian Arctic stratosphere, the same level, 10 hectopascals, rose by 63 degrees Celsius above the climatological mean in approximately 72 hours. The baseline was minus 80 degrees Celsius. The measured temperature briefly reached minus 17, a 63-degree anomaly in the stratosphere in 72 hours in January. This is what atmospheric scientists call a major sudden stratospheric warming event. The data says it was among the strongest in the satellite era, which begins in 1979. And the question it immediately raises, the question that drives every part of this investigation, is simple enough to state and complicated enough to take the next 120 minutes to answer fully. How fast does what happens 63 kilometers up become what happens in your living room? And what does it find when it gets there? The stratosphere is 63 kilometers above the Earth. The surface weather you experience, the wind, the rain, the temperature outside your window, happens in the troposphere, the lowest layer, extending from the ground to roughly 12 kilometers up. Those two layers are separated by the tropopause, a temperature inversion layer that acts as a partial barrier between them. For most of the year, what happens in the stratosphere stays in the stratosphere, but a sudden stratospheric warming event doesn't respect that boundary. The coupling mechanism works through two pathways operating simultaneously. The first is direct. A weakened stratospheric polar vortex no longer provides the upper-level support that keeps the tropospheric jet stream, the fast-moving river of air at roughly 10 kilometers altitude that steers surface weather systems, locked in its tight, high-latitude track. Without that support, the jet stream buckles southward in large waves. Cold, Arctic air that the jet stream normally keeps, penned to the north, is free to spill equatorward in what meteorologists call a Rossby wave-breaking event. The second pathway is more subtle. The warm, stratospheric anomaly alters pressure gradients that propagate downward through the atmosphere over days, further weakening the tropospheric circulation. The critical variable for this investigation is the lag time, the delay between the moment the stratospheric warming begins and the moment you feel it at the surface. Historically, that lag ranges from 10 to 21 days. Dr. Mark Baldwin at the University of Exeter, whose foundational work with Timothy Dunkerton in the year 2000 established the stratospheric-tropospheric coupling mechanism as a predictable and quantifiable relationship, described the lag as the window that gives forecasters time to warn the public, grid operators time to position resources, and infrastructure managers time to prepare. 10 days, 14 days at the mean, sometimes 21. The January 2024 event delivered surface impacts in 7 days. 7 days is not within the normal distribution of SSW to surface lag times. It falls in what researchers classify as the fast follower category, events where the downward propagation of the signal through the stratosphere and into the troposphere occurs at roughly twice the historical mean speed. The classification matters enormously for what came next, because the operational infrastructure that translates atmospheric science into human action, the forecast pipeline, the grid alert system, the consumer advisory chain, was not designed around a 7-day lag. It was designed around 14. The model disagreement compounded the problem. The ECMWF, the European Center for Medium-Range Weather Forecasts, whose ensemble system is widely regarded as the most accurate global atmospheric model for medium-range prediction, showed a 54% probability of a polar vortex split event in its Day 5 ensemble runs. The GFS, NOAA's global forecast system, showed 32% at the same lead time. That gap, 54 versus 32%, represents not a minor technical disagreement, but a fundamental uncertainty about whether a major disruption was about to occur. Grid operators receiving a 32% probability signal from the domestic model would apply a different level of preparedness than those receiving 54% from the European model. The difference between those two numbers, translated into operational preparation time, is measured in the same hours that ultimately determined how much margin the system had left. By the time both models converged on near certainty, by the time the forecast was unambiguous, the atmosphere had already committed to its path. The lobe was forming. The question of how fast it would arrive had already been answered by the physics. All that remained was for the infrastructure at the surface to either be ready or not. The record shows which it was. But before we get to that, the investigation requires a precise understanding of what exactly was descending toward the surface, because cold air doesn't capture it, not even close. Meteorologists have a vocabulary for what happens when a sudden stratospheric warming event disrupts the polar vortex sufficiently to displace a coherent mass of Arctic air southward. They call it a polar air outbreak. The term is accurate but insufficient. An outbreak implies something that escapes from containment. What the January 2024 event produced was something more organized, more dense, and more directional than an escape. It produced a lobe. A displaced polar lobe is a coherent, three-dimensional body of genuine Arctic air that originated over the Arctic Ocean and has been circling the pole at temperatures around minus 40 degrees Celsius at the 500 hectopascal pressure level, roughly 5.5 kilometers above the surface. When the vortex fractures in a split-type event, one of the daughter vortices is effectively ejected from the polar region and begins moving southward, maintaining much of its internal structure as it descends. It is not a cold front. A cold front is a boundary. A lobe is a volume. The descent accelerates for a reason that is counterintuitive until you understand the physics. As the lobe descends, the air within it is subjected to increasing atmospheric pressure. Adiabatic compression warms the air slightly, roughly 10 degrees Celsius per kilometer of descent for dry air. But the lobe's core temperature is so far below the temperatures of the air it's displacing that the compression warming is essentially irrelevant. A mass of air at minus 40 degrees that warms by 20 degrees through compression arrives at the surface at minus 20 degrees Celsius. In a region where the historical minimum temperature is minus 10 Celsius, minus 20 is not a cold snap. It is a structural failure event for every system calibrated to something warmer. The ASOS network, the Automated Surface Observing System, a joint FAA and National Weather Service program, with 1,800 stations distributed across the continental United States, recorded the lobe's arrival with the kind of granularity that turns atmospheric science into lived experience. At the station in Billings, Montana, on January 13, 2024, the temperature stood at 34 degrees Fahrenheit at 6 in the morning. By noon, it had reached 37. By 6 in the evening, it was minus 18 degrees Fahrenheit. 55 degrees of temperature change in 12 hours. 36 of those degrees fell in the final 4 hours. Denver's ASOS station recorded a 44 degree Fahrenheit drop in 4 hours. Rapid City, South Dakota dropped 38 degrees in 3 hours. These are not statistically improbable events in the context of the record. They are events for which the record has almost no comparison. The ASOS data flagged them as among the fastest temperature falls recorded at those stations since the network achieved its current density in the 1990s. Former NOAA chief scientist Dr. Ryan Mao has noted that rapid temperature falls of this magnitude are the most structurally damaging type of cold event for built infrastructure, for a reason that is rarely discussed in public coverage. Infrastructure is designed to survive a minimum temperature, not a rate of change. A building envelope, a pipeline, a water main. These systems are engineered to maintain structural integrity at their design minimum. They are not engineered for the thermal shock of transitioning from above freezing to far below freezing in the span of a single shift. The materials behave differently under rapid thermal stress than under gradual cooling. Metal contracts faster than insulation can accommodate. Pipes that would survive a slow drift to minus 20 can fracture when the temperature drops 30 degrees in 3 hours. The lobe wasn't just cold, it was fast. And fast in the context of infrastructure designed around historical norms that the lobe had never previously violated, is the mechanism that turns a weather event into a catastrophe. The North American electrical grid is 3 grids. The Eastern Interconnection covers most of the country east of the Rockies. The Western Interconnection covers the western states and part of Canada. And then there is the Texas Interconnection, also known as ERCOT, the Electric Reliability Council of Texas, which covers most of the state of Texas and is, by design, electrically isolated from the other 2. That isolation is not an accident or an oversight. It is a deliberate political and regulatory decision with roots in the Public Utility Holding Company Act of 1935, which imposed federal oversight on interstate electricity transactions. Texas, characteristically, declined to participate in interstate commerce, keeping its grid intrastate to avoid federal regulation. The practical consequence of that decision 9 decades later is that when ERCOT's generation capacity fails, there are no power lines connecting Texas to the rest of the country's electricity supply. Texas cannot import power from Louisiana. It cannot import power from New Mexico. It is electrically an island. In February of 2021, Winter Storm Uri tested that island's self-sufficiency and found it catastrophically insufficient. At peak, 33,000 megawatts of generation went offline simultaneously, roughly 37% of ERCOT's total generation on capacity. 4.5 million Texas households lost power. Many of them lost heat. The economic damage was estimated by the Texas Comptroller's Office at $195 billion. The direct death toll, per the Texas Department of State Health Services, was 246 people. Subsequent academic analysis, including work by Dr. Rachel Piltner and the Alamo Area Council of Governments, revised the excess mortality estimate to between 700 and 1,000 deaths when indirect causes are included. The policy response was the Public Utility Commission of Texas's Rule 25.55, adopted in April of 2021. The rule mandated 46 specific winterization measures across all thermal generation facilities in ERCOT. Pipe insulation, heat tracing for condensate systems, instrument winterization, equipment enclosures. The measures were categorized by priority. A compliance timeline was established. Audits were scheduled. The December 2023 PUCT audit report found that 38% of thermal generation facilities were fully compliant with all 46 required measures. 62% were not. The most consequential categories were the most technically critical. Instrument winterization, which covers the sensors and control systems that manage generator output in cold conditions, showed a compliance rate of 31%. Heat tracing for condensate knockout systems, the equipment that prevents produced water from freezing in gas fuel supply lines, showed 29% compliance. The mechanism by which non-compliant generators evaded formal consequences is documented in the audit's Appendix B. 61% of non-compliant generators submitted what the PUCT framework calls reasonable progress reports in lieu of completed compliance certifications. The reasonable progress mechanism was intended to accommodate generators making genuine upgrades on a defined timeline. In practice, it became a documented pathway for indefinite non-compliance. As of the December 2023 audit cycle, conducted 1 month before Winter Storm Heather, the PUCT had assessed $0 in financial penalties for weatherization non-compliance. PUCT Commissioner Cobos noted this in a dissenting statement attached to the audit. Beth Garza, who served as ERCOT's independent market monitor for a decade and has testified before the Texas Senate Business and Commerce Committee on Grid Reliability, has said publicly that enforcement without consequences is not enforcement. The audit confirmed that the gap between the mandate and the reality, between what Uri required and what generators actually built, remained wide, documented, and unpenalized 32 months after the mandate was issued. The lobe was descending. The grid it was descending toward was 62% unfinished. Everything runs on natural gas in a Texas winter. The furnaces in the houses, the commercial boilers in the hospitals, the industrial burners in the refineries, and, critically, Fundamentally, in a way that is rarely explained in public coverage of grid events, the turbines that generate roughly 40% of ERCOT's winter electricity. Natural gas is not just a fuel for heating. It is the fuel that generates the power that keeps every other system alive. When the gas stops flowing, it doesn't just turn off the furnaces. It turns off the generators that run everything else. The U.S. produces approximately 103 billion cubic feet of natural gas per day, according to the Energy Information Administration's 2023 annual average. The Permian Basin in West Texas and southeastern New Mexico accounts for roughly 20% of that total, about 20 billion cubic feet per day. Together with the Haynesville Shale in Louisiana and the Marcellus in Pennsylvania, these three basins supply the fuel that heats northern cities through southern pipelines, runs the turbines that generate electricity for the entire eastern half of the country, and maintains pressure in a distribution network that touches every household with a gas meter. Natural gas, as it comes out of the ground, contains produced water, water vapor, and liquid water that travels with the gas through the wellbore. In the surface equipment, the separators, the meter runs, the compressor inlet lines, that produced water can freeze. When it freezes, it blocks the equipment. The well stops producing. The technical term is wellhead freeze-off. The temperature at which freeze-offs begin in non-winterized equipment is approximately 20 degrees Fahrenheit, according to the Department of Energy's 2021 analysis of the Uri event. This is not a temperature that surprises operators in Alberta or North Dakota, where Arctic-grade equipment is standard and wellhead winterization is a baseline operational requirement. But Texas wells were not built to Arctic specifications, because the historical minimum temperature at Midland, Texas, the heart of the Permian Basin, was 9 degrees Fahrenheit, recorded in 1989. 32 years passed between that record and Uri. 32 years of wells designed to survive a minimum of 9 degrees. Uri brought minus 2 degrees Fahrenheit to Midland on February 11, 2021. 11 degrees below any temperature the Permian Basin had ever recorded in the instrumental era. At that temperature, equipment designed for 9 degrees above zero didn't gradually degrade. It stopped. The supply cliff was documented in real time by the Texas Railroad Commission, which regulates oil and gas production in the state. At peak, 25 billion cubic feet per day of gas production was removed from the supply network by wellhead freeze-offs and associated equipment failures. Against a total national daily production of approximately 103 billion cubic feet, that is roughly 24% of the entire U.S. daily natural gas supply, gone in 48 hours. Now connect that number to the grid. 40% of ERCOT's winter generation capacity is gas-fired. When the gas supply contracts by 24%, the gas turbines don't run at reduced capacity. They run until their fuel supply pressure drops below operating minimums, and then they shut down. Not a reduction, a shutdown. And every gas turbine that shuts down for lack of fuel is a gas turbine that cannot be brought back online by fixing the weatherization on the generator. The weatherized generator cannot run without gas, and the gas cannot flow until temperatures rise enough to thaw the wellhead equipment. This is the cascade that Uri ran. This is the sequence that the investigation now turns to in full. Because understanding how the gas grid feedback loop operates in real time is essential to understanding why the compound failure described in the next section is not a theoretical worst case. It is a documented historical event that the January 2024 SSU forcing conditions were capable of rerunning on a grid that was still 62% unfinished. But first, there is a third system underneath all of this, buried under every street in every city in the path of the lobe. Pressurized aging, designed for temperatures that the lobe was about to violate by margins that no municipal engineer had ever planned for. And unlike the grid and the gas network, this system has no load shedding protocol, no controlled failure mode. When it goes everywhere, simultaneously, and it comes back last. To understand what the January 2024 event actually looked like in the data, to read it the way the scientists who study this read it, you need to spend a few minutes with the instruments, because the stratosphere is not accessible by weather balloon at the altitudes that matter here. The 10 hectopascal pressure level, where the polar vortex diagnostic is measured, sits at approximately 31 kilometers above the surface. Standard radiosonde balloons reach roughly 35 kilometers before they burst, but their data quality degrades significantly above 25. The primary data source for stratospheric monitoring in the modern era is satellite-derived reanalysis. Specifically, the MERA-2 dataset produced by NASA's Global Modeling and Assimilation Office at Goddard Space Flight Center. MERA-2 stands for the Modern Era Retrospective Analysis for Research and Applications, version 2. It is not a forecast model. It is a reanalysis, a reconstruction of the state of the atmosphere using the best available observations, assimilated through a numerical weather prediction model, spanning from 1980 to the present with hourly temporal resolution and approximately 50-kilometer horizontal resolution. When atmospheric scientists want to place a current event in historical context, MERA-2 is the reference dataset. And what MERA-2 recorded for the January 2024 event is unambiguous. The 10 hectopascal temperature anomaly over the Canadian Arctic, the difference between the observed temperature and the climatological mean for that date and location, reached plus 63 degrees Celsius on January 21st, 2024. The climatological mean temperature at that altitude and location in late January is approximately minus 80 degrees Celsius. The observed temperature on that date was approximately minus 17 degrees Celsius. A layer of atmosphere that should be minus 80 was minus 17. The warming was not confined to a small area. MERA-2 showed the anomaly covering a region of several million square kilometers centered on the Canadian Arctic. Simultaneously, the zonal mean wind, the average west to east wind, speed around the entire 60-degree north latitude circle at the 10 hectopascal level, reversed from plus 32 meters per second to minus 18 meters per second over 72 hours. Plus 32 is a normal, healthy westerly polar vortex wind. Minus 18 is a sustained easterly reversal. The sign change alone defines the event as a major sudden stratospheric warming. The magnitude, 50 meters per second of change in 72 hours, places it in the top tier of the historical record. Dr. Diana Domison at ETH Zurich, whose research into the teleconnection between SSW events and surface weather patterns has refined our understanding of which events produce strong surface impacts and which do not, has categorized SSW events by type as a predictor of surface impact strength. The two primary types are displacement events, where the polar vortex shifts off the pole but remains intact, and split events, where the vortex divides into two daughter vortices. The January 2024 event was classified as a split. According to the climatology published by Domison and Butler in 2021, split events produce a below normal temperature signal over eastern North America in 67% of cases within 14 days of SSW onset. Displacement events produce that signal in only 40% of cases. The split classification is therefore not a technical detail. It is a probabilistic statement. The type of event that occurred in January 2024 was the type most likely to send its surface signal southward, toward the continental United States, within the operational window before the infrastructure of that surface could prepare. Historical context places the event in sharper relief. In the satellite era since 1979, approximately 6 major SSW events occur per decade in the Northern Hemisphere. Approximately 40% of those are split type, roughly 2 to 3 per decade. The January 2024 event was the most recent split event in the record at the time of this investigation. The previous one of comparable stratospheric anomaly magnitude was the event that drove Winter Storm Uri in February of 2021. The one before that was February of 2019, 3 split-type major SSW events in 6 years, where the historical mean was approximately 1 every 3 to 4 years. Whether that represents a meaningful trend or natural variability is an active research question. What it represents operationally is that the scenario described in this investigation is not rare. It has happened 3 times in 6 years. The MERA-2 data is public. The zonal mean wind reversal is public. The temperature anomaly is public. The split type classification is documented in the scientific literature within days of the event. Any grid operator with access to a working relationship with an atmospheric scientist had access to this information at the moment it mattered. The question that drives the next section of this investigation is what the pipeline between that information and the people who operate the grid actually looks like, and where it delays. Here is where the investigation takes a turn that most people haven't heard, because the story of the January 2024 polar vortex event is not simply a story about a natural atmospheric phenomenon and its consequences. It is a story about the gap between what the atmosphere was telling us and when we were institutionally prepared to act on it. And that gap, when you measure it in the hours and days that determine the system's margin, is the most important finding in this investigation. NOAA's Climate Prediction Center issues 2 operational temperature probability outlooks that are relevant here. The 6 to 10 day outlook provides temperature probability for the period 6 to 10 days from the issue date. The 8 to 14 day outlook provides temperature probability for the following week. Both are issued daily and are publicly available. These outlooks are the primary input into medium range infrastructure planning for grid operators, gas pipeline schedulers, and emergency management agencies across the country. The CPC 8 to 14 day outlook for the period January 20th through January 26th was issued on January 6th. The SSW event onset was January 21st. That means at 14 days lead time, the CPC outlook showed not a high probability cold signal, but equal chances of above normal, near normal, or below normal temperatures across the central United States. EC in the probability grid language. Equal chances. The standard formulation when the models are uncertain. On January 13th, 7 days before the surface impact, the outlook was updated to likely below normal with 33 to 50% probability for the central U.S. On January 16th, 4 days before the surface impact, it was updated to probably below normal, with probabilities exceeding 50% in some areas. The formal ERCOT weather watch was issued on January 15th. The conservation appeal requesting voluntary demand reduction from Texas consumers was issued January 22nd, the same day the lobe's coldest air reached the surface. Map those dates onto the operational timelines of the systems that needed to respond. ERCOT requires generation units to submit unit availability reports 4 days ahead of need, the 4-day operational window. Natural gas pipeline operators use 48 to 72-hour weather forecasts for supply pre-positioning decisions. Moving gas into line pack, the volume of gas stored under pressure in the pipeline itself, ahead of anticipated demand spikes. Municipalities begin consumer advisory communications based on National Weather Service winter storm watches and warnings, which are typically issued 48 to 36 hours before event onset. Every one of those operational windows is shorter than the scientific signal. The SSW event was detectable in the MERA-2 data at the moment of onset, January 21st. The ECMWF ensemble showed a 54% probability of a vortex split at day 5, January 16th, 5 days before the surface impact. But the formal institutional signals, the grid watch, the pipeline pre-positioning alerts, the consumer advisories were tied to the shorter operational windows that the institutional pipeline was designed around. Dr. Judah Cohen has argued in public writing that SSW to surface lag understanding should be incorporated into grid operational alerts at the 10 to 14 day lead time, that the science now exists to justify raising a formal grid preparedness alert based on a stratospheric wind reversal days before the surface signal is certain. As of the time of this investigation, no NRC standard or ERCOT protocol incorporates a stratospheric diagnostic as a trigger for operational alerts. The scientific signal and the institutional response system are running on different clocks. The scientific clock is 14 days. The institutional clock is 4 days. And in January of 2024, the difference between those two clocks was measured in the preparation time that either was or wasn't done before the lobe arrived. Is this a physics problem? The inherent uncertainty of medium-range atmospheric prediction? Or a communication problem? the institutional pipeline's inability to translate a probabilistic scientific signal into a risk-proportionate operational response? The answer the data supports is that it is both, and that the distinction matters less than the consequence. A grid that knew, statistically, at 5 days, that it was likely facing a major cold event received its formal preparedness mandate at 4 days, with half the lead time that the atmospheric science could theoretically have provided. That gap is where the next failure lives. And the next section of this investigation shows exactly how that gap expresses itself when the gas supply and the grid are running simultaneously toward the same cliff. And this is where the story takes a turn that most people haven't heard about. Because the cascade is not a sequence of separate failures. It is a feedback loop. And the February 2021 event ran that loop all the way to the edge of a catastrophe that would have made Uri look like a dress rehearsal for something unimaginably worse. Here's the sequence in the order it actually occurred. February 8th, 2021. Temperatures begin dropping below 20 degrees Fahrenheit across the Permian Basin. Wellhead freeze-offs begin. Individual wells start failing. Gas supply to the interstate pipeline network starts contracting. February 9th. Gas-fired generation units in ERCOT begin receiving reduced fuel supply. Some units begin derate, reducing output to match available gas. Others, on firm gas contracts with priority delivery, hold full output. The total generation picture starts deteriorating, but not yet dramatically. February 10th. The storm intensifies. Gas supply loss accelerates. By mid-morning, ERCOT is managing a shortfall that its reserves can cover. By mid-afternoon, the shortfall exceeds its operating reserve. At 10:37 in the evening, ERCOT's frequency, the measure of grid stability, the number that must stay within a narrow band around 60 Hz for the alternating current grid to function, drops to 59.3 Hz. Normal operating range is 59.9 to 60.1. The ERCOT system frequency at 10:37 was 0.7 Hz from the lower boundary of controlled operation. Below 58.5, automatic protective relays would begin tripping generation and load offline in sequences designed to protect equipment, sequences that, once initiated, can take the grid from partial failure to total uncontrolled blackout in minutes. ERCOT's post-event analysis states that at 10:37 on February 10th, the system was approximately 90 seconds from initiating that cascade. 90 seconds from a total, uncontrolled blackout that their own engineers estimated would have required 4 to 6 weeks to restore from scratch. Not 4 to 6 days, 4 to 6 weeks. For 4.5 million households in winter, at temperatures below zero. The system pulled back. Controlled load shedding, rolling blackouts, were implemented and held frequency above the critical threshold. But the controlled blackouts were not controlled for long. As temperatures dropped further, demand continued to rise faster than generation could recover. The rolling blackouts became extended outages, gas compression stations, the equipment that maintains pipeline pressure in the distribution network began losing power. Without power, the compressors couldn't run. Without compressor pressure, gas distribution pressure in local lines dropped below operating minimums. Furnaces in homes with gas heat began failing, not because the gas supply was interrupted, but because the pressure was insufficient to operate the burner control valves. People with gas heat and working gas lines had no heat because the electrical system that powered the gas distribution network's compressor stations was down. The feedback loop was complete. The grid depended on gas. The gas distribution network depended on the grid. Each system's failure accelerated the others. Now, close the compliance loop from Part 4. The December 23 PUCT audit found 38% fully compliant with weatherization mandates. Instrument winterization, 31% compliant. Heat tracing for condensate systems, 29% compliant. These are not peripheral systems. Instrument winterization covers the sensors and control systems that tell a generator how much fuel it's receiving and how to adjust output accordingly. Heat tracing for condensate systems is the equipment that prevents wellhead-produced water from freezing in the gas fuel supply lines before it reaches the burner. A generator with 31% instrument winterization compliance doesn't shut down cleanly when temperatures drop. Its control systems malfunction unpredictably. It derates erratically. It can trip offline on a protective fault rather than a controlled shutdown, and a tripped generator takes longer to restore than a controlled derate. The January 2024 Winter Storm Heather tested this system with a displacement type SSW event, less severe than the January split event, but real enough to put 6,200 megawatts of ERCOT generation offline at peak, 6,200 megawatts against an 80,000 megawatt system. The system survived. The operating reserve at minimum was approximately 2,400 megawatts, 3% of total demand, against NRC's recommended minimum of 15%. That 12-point gap, 9,800 megawatts of additional reliable generation, was the difference between what Heather delivered and what a full split-type polar lobe was capable of demanding: 246 direct deaths, 700 to 1,000 excess deaths, 4.5 million households without power, 90 seconds from a 4 to 6 week total blackout. That was Uri on a system where the SSW forcing was comparable to, though slightly less intense than, the January 2024 split event. With weatherization mandates in place, mandates that 38% of generators had met 2 years and 9 months later. The cascade mechanism is not theoretical. It ran. The only open question, the question the data forces but cannot yet answer, is what the forcing conditions of the January 2024 SSW event would have done to a grid that survived Heather at 3% reserve. Underground, under every street in the path of the polar lobe, there is a system that carries no electrical load, generates no frequency signal, and appears in no grid operating report. It is buried specifically to be invisible, to run without attention, to deliver water at pressure to every household and hospital, and fire hydrant in the city perpetually without anyone thinking about it, until the ground temperature drops below 32 degrees Fahrenheit to the depth at which it's buried. At that point, a water main doesn't gradually degrade, it fails. And it fails in a way that is uniquely catastrophic in a compound infrastructure event. It fails everywhere at once. The frost line, the depth to which the soil temperature drops to 32 degrees Fahrenheit during a historically severe winter, is the engineering parameter that determines how deep water mains are buried. In Minneapolis, the frost line is approximately 42 inches. In Chicago, 36 inches. In Dallas, approximately 14 inches. In Houston, 6 to 8 inches. In cities along the Gulf Coast, the design standard assumes the soil will never reach freezing temperatures below the first few inches of the surface layer. Those design standards are calculated from historical climate data, the deepest frost penetration observed in the local instrumental record. They do not account for temperature events outside that record. They do not account for a polar lobe delivering surface temperatures that have never previously occurred at that location. The USGS soil thermal diffusivity model, derived from the foundational soil physics work of Rawls and colleagues, provides a way to project how deep a given surface temperature, sustained for a given duration, will drive the frost line into different soil types. In sandy loam, which characterizes much of the Texas soil column, 48 continuous hours of minus 10 degrees Fahrenheit surface temperature can drive the frost line 22 inches deeper than its historical maximum. In Houston, where the historical frost line is 6 to 8 inches, and the frost line design standard assumes a minimum surface temperature of 15 degrees Fahrenheit, Uri delivered 12 degrees Fahrenheit for 22 continuous hours. The frost line penetrated to depths the pipes were not designed to survive. Austin Water's post-event report documented 400,000 service disruptions following Uri, affecting roughly half the city's customer base. The cost of infrastructure repair was estimated at approximately $1 billion. Dallas water utilities recorded 900 main breaks during the Uri period, against a pre-event annual average of 350. The previous annual record was 420 breaks. Dallas experienced more than twice its record annual average in a single event. The TCEQ, the Texas Commission on Environmental Quality, documented boil water notices across hundreds of Texas public water systems during and after Uri. Austin's boil water notice lasted 12 days after grid power was restored. Some smaller systems were under boil water notices for 28 days after the storm. The 12-day lag between grid restoration and water safety restoration is critical to understanding the compound event mechanism. When water pressure drops across an entire city simultaneously, when hundreds of mains break within hours of each other, the repair operation confronts a logistics problem with no parallel in normal operations. A typical water main break is repaired by a crew with equipment, excavating a contained area, making the repair, restoring pressure, and moving on. A simultaneous 900 break event means 900 excavation sites competing for the same pool of crews, the same equipment, the same materials, and every repair requires working water pressure in adjacent lines to test and restore the repaired segment, which is unavailable when hundreds of adjacent segments are also broken. The hospitals and dialysis centers and fire suppression systems that depend on water pressure during those 12 days are not waiting for a sequential restoration process. They are waiting for a simultaneous restoration process that the water system's mutual aid compacts cannot accelerate. The water system doesn't fail after the grid and gas fail. It fails at the same time. And it comes back last. 3 systems, 3 simultaneous failures, 3 separate restoration timelines that cannot be parallelized because each one depends on the others. That is the compound event. And the next part of this investigation turns to what the response to that compound event actually looks like, and what the evidence says about how prepared the country is to manage it again. Emergency management in the United States is built on a concept called the Incident Command System, a hierarchical, modular framework developed after the catastrophic coordination failures of the 1970s California wildfires and codified into federal doctrine after September 11th of 2001. It is an excellent system for managing single incidents with a defined perimeter, a defined impact area, and a defined set of resources that can be mobilized, deployed, and tracked. It was designed for fire, for flood, for hurricane, for events that happen in a place, affect a region, and can be surrounded by response capacity mobilized from outside the affected zone. A compound, cascading infrastructure failure covering multiple states simultaneously is not that kind of incident. It is something the Incident Command System was not designed to manage, not because the system is inadequate, but because the scenario was not the design basis. FEMA's National Response Framework was updated in 2022. The update included, for the first time, a dedicated section on compound events. That section is 2 pages long. The total document is 512 pages. The compound event section was added in direct response to Uri. It acknowledges that simultaneous multi-sector failures require enhanced interagency coordination and pre-positioned resources. It does not specify what those resources are, where they are pre-positioned, or what the trigger threshold is for deploying them. The National Academies of Sciences, Engineering, and Medicine published a report in 2023 titled Resilience of the U.S. Electrical Power System Under Extreme Weather Events. The report recommended that compound event planning be elevated from a secondary consideration to the primary design standard for grid infrastructure resilience. As of the time of this investigation, that recommendation has not been implemented as policy by either FERC, ERCOT, or the Department of Energy. Dr. Emily Grubert at Georgetown University has written that the mutual interference problem, the way each system's failure blocks the repair of the others, is the defining feature of compound infrastructure events that existing response doctrine does not adequately address. The electrical crews who restore the grid need shelter and heat to operate safely. Water repair crews need electricity for pump stations and equipment. Gas infrastructure crews need water for safety protocols. In a compound event, none of these inputs are available. Each repair stream is blocked by the failure it is trying to fix in another stream. The electric sector regional response groups, the ESRGs, are the mutual aid compacts for grid restoration. When a state loses significant generation capacity, it can request aid from neighboring states through the ESRG framework. Crews, equipment, mobile generation assets. The framework worked in the aftermath of hurricanes that hit a single state while neighboring states retained their intact infrastructure. It was stress tested by Uri in ways it was not designed for. Texas's isolation as a separate interconnection meant it couldn't receive power imports, only crews and equipment. The crews and equipment that arrived couldn't generate electricity. They could only help restore the transmission infrastructure once generation came back online. And the generation couldn't come back online until the gas wells thawed, which happened when temperatures rose, which happened on the weather's timeline, not the ESRGs. The mutual aid framework, in other words, was not the constraint. The constraint was the sequential dependency of the restoration process. Gas first, then generation, then grid frequency, then distribution, then water pressure. Each step required the previous one. And each step was measured in days, not hours. The response to a full split-type polar lobe event across a grid that is 38% weatherization compliant would run that same sequential restoration timeline. The question that the next section answers from the historical record is how long that timeline actually takes. The detailed timeline of Winter Storm Uri is available in the public record. It is available in ERCOT's post-event analysis, in the FERC-NERC joint investigation published in November of 2021, in the Texas Comptroller's Economic Impact Statement, in the City of Austin Water post-event report published April 2021, and in the academic literature. It is a complete, documented, time-stamped account of exactly what the compound failure cascade looks like when it runs from onset to recovery. The reason it is worth revisiting in detail, the reason this investigation has spent considerable time establishing the mechanism before returning to the historical record, is that the template is only legible once you understand the mechanism. Now you do? February 8th, Permian Basin. Temperatures drop to the low 20s Fahrenheit. First wellhead freeze-offs begin. Gas supply contracts begin falling below nomination volumes on the interstate pipeline network. February 9th, gas-fired generation units in ERCOT begin receiving reduced fuel. Some units begin derate. ERCOT's real-time energy market shows supply margin narrowing. No formal watch or warning issued. The operational picture is deteriorating but manageable under existing reserves. February 10th, the supply cliff. Gas production losses accelerate to the scale described in Part 5, approximately 25 billion cubic feet per day removed from the national supply network. By evening, generation shortfall exceeds operating reserves. At 10:37 p.m., the grid frequency reaches 59.3 Hz, 90 seconds per ERCOT's own analysis from a total uncontrolled blackout. Controlled load shedding is implemented. February 11th, the controlled load shedding fails to hold against continuing demand as temperatures reach their nadir. The rolling blackouts extend beyond their planned duration. Gas compression stations begin losing power. Local gas distribution pressure begins dropping. 4.5 million households are without power. This is day 3, February 12th through 14th. Peak outage period. Temperatures at their lowest. Gas supply at its minimum. Grid generation at its minimum. Water main failures begin. Ground temperatures in Dallas drop below the frost line design depth. Austin reports hundreds of main breaks. Dallas reports the first wave of 900 total breaks. The water system enters failure mode simultaneously with the grid and gas systems. February 15th. Temperatures begin rising. Gas wellhead equipment begins thawing. Gas production begins recovering. Grid generation begins recovering. ERCOT begins reducing load shedding. Power is restored to most customers over the following 24 to 48 hours. This is day 7, February 15th to 22nd. Grid is substantially restored. Gas supply is substantially restored. The water system is not. The 900 broken Dallas mains require excavation, repair, pressure testing, and restoration one by one. Austin is under a boil water notice. The repair crews are working, but 900 breaks, competing for finite crews and equipment and materials, in conditions that are still below normal. The restoration is linear, not parallel. It cannot be accelerated by adding resources beyond a certain threshold, because the excavation sites are geographically distributed and each requires a separate crew and equipment set. February 22nd, Austin's boil water notice is lifted, 12 days after the grid came back. The last boil water notices in the Texas system, in smaller communities with more severely damaged distribution infrastructure, were lifted 28 days after the storm's peak. The template tells us three things about the timeline. Gas and grid restoration, approximately 5 to 7 days from temperature nadir to substantial recovery. Water system restoration, 12 to 28 days after grid restoration, depending on the severity of distribution infrastructure damage. Total compound event duration from onset to full system restoration, 3 to 5 weeks. That is the historical timeline. That is what the record shows. Dr. Andrew Dessler at Texas A&M has noted that the policy window, the period after Uri, during which public attention and political will were aligned to mandate and fund weatherization, was approximately 18 months. By late 2022, the urgency had faded. The reasonable progress mechanism was in full operation, and the PUCT's December 2023 audit found the grid still 62% unfinished, 32 months after the mandate. The 46 weatherization measures mandated under PUCT Rule 25.55 cover 4 categories: pipe and equipment insulation, heat tracing for fluid carrying systems, instrument and control, winterization, and facility enclosures for equipment housing. Each measure has a specific compliance criterion, not a general requirement to protect against cold, but a defined specification. The December 2023 audit examined these 46 measures at every thermal generation facility operating within the ERCOT footprint. The overall finding, 38% fully compliant, breaks down in ways that matter for understanding where the real exposure is. The highest compliance category was pipe and equipment insulation. Approximately 68% of facilities had completed all required insulation measures. These are visible, physical improvements, adding insulation to pipes that can be seen and measured. They are relatively inexpensive, require no ongoing power supply, and fail passively rather than actively. A pipe that is under-insulated loses heat more quickly than a properly insulated pipe, but the failure mode is gradual. The lowest compliance categories were the ones with the most consequential failure modes. Instrument and control winterization, covering the temperature sensors, pressure transmitters, and control systems that operate the generator in cold conditions, showed 31% compliance. Heat tracing for condensate knockout systems, the electrically powered heat cables that keep produced water from freezing in the gas fuel supply lines upstream of the burner, showed 29% compliance. These are the systems that fail actively. A malfunctioning temperature sensor gives the generator control system incorrect data. A failed heat trace cable allows ice to form in the condensate separator, blocking gas flow to the burner. These failures don't reduce output. They produce trips, abrupt, uncontrolled shutdowns, that take the unit offline on a protective fault. The enforcement mechanism's absence is documented with equal clarity. Appendix B of the December 2023 audit lists each non-compliant facility and its compliance pathway. Of the 62% non-compliant, 61% submitted reasonable progress substitutes. The reasonable progress mechanism requires a generator to document what work has been completed and what work remains. It does not require the generator to meet any interim milestone. It does not trigger any financial penalty. The only consequence of filing a reasonable progress report is that the generator must file another reasonable progress report at the next audit cycle. Commissioner Kobos's dissenting statement attached to the audit used the phrase accountability without consequence to characterize the reasonable progress mechanism. Beth Garza, testifying before the Texas Senate Business and Commerce Committee in February of 2024, said that mandating weatherization without enforcing the mandate is indistinguishable from a reliability standpoint from not mandating it at all. The institutional delay pattern that runs through this investigation, the stratospheric signal available at 14 days but acted on at 4. The weatherization mandate issued 32 months before the audit, but still 62% incomplete, is a structural feature of the system between the science that identifies the risk and the institutions assigned to manage it. The delay is not malicious. It is not the product of ignorance. It is the product of a compliance pipeline designed around the assumption that the next major event will not arrive before the process completes. Uri demonstrated that assumption was wrong. The December 2023 audit confirmed that the assumption had not changed. And then, 1 month later, Winter Storm Heather arrived to provide the first direct test of the partially winterized grid. January 22, 2024, the polar lobe, the displacement-type Arctic air mass, driven by the January SSW event, reached the surface across the central United States. Dallas-Fort Worth. International Airport recorded a low of 3 degrees Fahrenheit, the coldest temperature at that station since the Uri event. The sub-10-degree period lasted 11 hours. This is relevant because the Uri sub-10-degree duration at DFW was 31 hours, nearly 3 times as long. Heather was a real event. It was also relative to what the January SSW forcing conditions were capable of producing in a full split-type configuration, a partial event. ERCOT's operational response began with the January 15th weather watch, 7 days before the coldest air arrived. The January 22nd Conservation Appeal requested voluntary demand reduction from Texas consumers. Between those 2 dates, grid operators worked to maximize available generation, contact generating units about their availability, and position the system's reserves as favorably as possible within the 4-day operational window. At peak demand during Heather, ERCOT was managing a shortfall. The total generation enforced offline by cold weather equipment failures reached 6,200 megawatts, against an 80,000 megawatt system that represents 7.8% of total generation at capacity. The system's operating reserve at the minimum, the buffer between total available generation and total demand, was approximately 2,400 megawatts, 3%. NERC's minimum recommended operating reserve for ERCOT is 15%. At 15% of an 80,000 megawatt system, that minimum reserve is 12,000 megawatts. The actual reserve during Heather was 2,400 megawatts. The gap between actual and recommended reserve was 9,600 megawatts. ERCOT did not implement rolling blackouts during Heather. The system held, but 3% was the thinnest margin at which the system has operated without blackouts since Uri. NERC, in its winter reliability assessment published in November of 2023, 6 weeks before Heather, flagged ERCOT as being at high risk for generation adequacy under elevated demand scenarios. The same assessment flagged MISO, the Mid-Continent Independent System Operator, covering a 14-state region from Montana to Louisiana, as elevated risk. It flagged SPP, the Southwest Power Pool, covering the central U.S. from North Dakota to Oklahoma, as elevated risk. 3 of the 5 major grid regions in the continental United States were identified as carrying elevated or high reliability risk for the winter season, before the winter season began, by the Federal Reliability Organization responsible for overseeing them. The Heather event confirmed the NERC assessment. The system survived with a 3% reserve, 12 points below the recommended minimum. And the event that produced that 3% reserve was a displacement-type SSW response, a weaker surface response than a split-type event produces, against a grid that was 38% weatherization compliant. The data assembles its own conclusion. The investigation does not assemble it for you. But the next section, the honest assessment of 3 interpretations, will name what the data supports and what it doesn't. Because this investigation does not reach conclusions the evidence cannot reach, and it does not withhold conclusions the evidence clearly supports. Before the 3 interpretations framework, before the honest assessment of what the evidence supports and what it doesn't, this investigation needs to address something directly, because the topic of polar vortex disruption attracts a specific category of fringe explanation that circulates widely on social media, that gets attached to legitimate coverage of real atmospheric events, and that is worth addressing with the same rigor the investigation has applied to everything else, not with dismissal, not with condescension, but with physics. The most common fringe claim attached to polar vortex disruption events is weather manipulation. The specific mechanism most frequently cited is HARP, the High Frequency Active Auroral Research Program, a research facility located near Gakona, Alaska, that operates a phased array of radio antennas used to study the ionosphere. The claim, in its most common form, is that HAARP can heat the ionosphere in ways that alter stratospheric circulation, disrupt the polar vortex, and direct extreme weather events as a tool of geopolitical coercion. I want to address this directly because it deserves an honest answer grounded in physics, not just dismissal. HAARP's maximum radiated power output is 3.6 megawatts. The facility, now operated by the University of Alaska Fairbanks, and whose technical specifications are publicly documented, can produce a focused radio beam of 3.6 megawatts directed into the ionosphere, the layer of the atmosphere above approximately 60 kilometers altitude. The ionosphere is above the stratosphere. HAARP's mechanism of interaction is the absorption of radio frequency energy by free electrons in the ionosphere, producing localized heating of approximately a few thousandths of a degree Celsius in a region roughly 10 kilometers across. The stratospheric polar vortex is a planetary-scale wind system. Its kinetic energy budget, the total energy contained in the wind system that must be disrupted to produce a sudden stratospheric warming event, is on the order of 10 to the 22nd joules. That number is 10 followed by 21 zeros. It represents roughly the kinetic energy of 2 million nuclear weapons detonated simultaneously. HAARP's 3.6 megawatts of radiated power, applied continuously for a full year, produces approximately 1.1 times 10 to the 14th joules of total energy output. HAARP would need to operate at its current power for approximately 900 trillion years to deliver the energy required to produce a single SSW event through direct energy deposition. The age of the universe is approximately 13.8 billion years. The physics makes the claim impossible, not improbable, impossible, by a margin so large that no classified upgrade to the facility could bridge it. The energy gap is not a technical limitation of current technology. It is a statement about the scale of atmospheric systems relative to any energy source that human civilization has constructed or could construct. The impulse behind the claim, the desire for an explanation that assigns agency and intentionality to events that feel too large and too consequential to be purely natural, is understandable. The frustration with institutional communication that downplays risk while the data tells a different story is legitimate. These are reasonable responses to the situation this investigation has been describing. The conspiracy explanation is wrong. The impulse behind it is not. Here is what the actual evidence shows about the human fingerprint on polar vortex disruption. The Arctic has warmed at approximately 4 times the global mean rate since 1979, according to the IPCC's 6th assessment report, published in 2021. The global mean surface temperature has increased by approximately 0.8 degrees Celsius over that period. The Arctic mean temperature has increased by approximately 3.1 degrees Celsius. This phenomenon, Arctic amplification, is the documented peer-reviewed, satellite-confirmed consequence of greenhouse gas forcing on a polar region that loses its reflective sea ice cover as temperatures rise, absorbs more solar energy, warms further, and loses more ice in a feedback loop that has been observed, measured, and modeled for 4 decades. Dr. Jennifer Francis at the Woodwell Climate Research Center has produced a body of research examining how Arctic amplification affects the temperature gradient between the Arctic and the mid-latitudes, the same gradient that maintains the strength of the polar vortex. A warmer Arctic means a reduced temperature gradient. A reduced temperature gradient means a weaker vortex. A weaker vortex is more susceptible to disruption by upward propagating wave activity. The connection between greenhouse gas forcing, Arctic amplification, and polar vortex disruption is an active research area with genuine scientific uncertainty about the magnitude of the effect. But the direction of the effect, warming, reduces the gradient that stabilizes the vortex, is consistent across the models and the observational record. The real human fingerprint is not a radio array in Alaska. It is 40 years of greenhouse gas accumulation that has altered the temperature structure of the Arctic atmosphere. in ways that are measurable, documented, and consistent with the physics. That mechanism doesn't need a conspiracy. The ordinary physics of what we have done to the composition of the atmosphere is alarming enough without embellishment. And unlike the HAARP theory, it comes with 4 decades of satellite data. The evidence assembled in this investigation supports 3 distinct interpretations of what it means for future risk. Each interpretation is grounded in the same data set. Each represents a coherent reading of that data set by a reasonable, informed analyst. The investigation presents all 3 fairly, because intellectual honesty requires it, and because only future events and the unreleased data identified in Part 16 will determine which interpretation is correct. Interpretation 1, the most generous reading of the data. The January 2024 SSW event was severe by historical standards, but the surface infrastructure performed within its design tolerances with margins that, while thin, were positive. ERCOT did not implement rolling blackouts during Winter Storm Heather. The 6,200 megawatts of lost generation were accommodated by the operating reserve, which, though below the NERC recommended minimum, was sufficient. The grid survived. The PUCT weatherization process, while slower than desired, is progressing. The 38% full compliance figure represents a real improvement from 0% compliance at the time of Uri, achieved against an industry that was starting from scratch. The 62% non-compliance figure includes facilities at various stages of completion. It is not 62% of facilities with zero progress, but 62% that have not achieved full certification. The compound failure cascade described in this investigation represents a genuine tail risk, a scenario that has occurred once, under conditions that will not recur identically. The system has demonstrated resilience and is improving. Interpretation 2. The intermediate position. The Heather stress test revealed a 3% operating reserve, 5 times below the NERC minimum, under forcing conditions that were significantly less severe than what a full split-type SSW event produces at the surface. The 38% weatherization compliance figure, against a December deadline that is now passed by more than 2 years, reflects a structural enforcement failure that the zero penalty finding confirms. Arctic amplification is a documented process operating continuously and will continue to increase the frequency and equatorward displacement of polar air outbreaks over the coming decades. A Uri equivalent event, historically occurring once every 15 to 20 years, occurring against the current preparedness posture of the ERCOT grid, would likely produce rolling blackouts across multiple service territories, with compound water system failures in cities that have not winterized their distribution infrastructure. Recovery would be measured in days to weeks, not hours. The risk is not catastrophic in the sense of a grid that cannot be restored. It is humanitarian in the sense of millions of people without heat, for days, in winter, with degraded water access. Interpretation 3. The most concerning reading of the data, the NERC Winter Reliability Assessment of November 2023 flagged not 1 but 3 of the 5 major North American grid regions as carrying elevated or high risk for generation adequacy under extreme cold conditions. This means that a continental scale polar lobe event, the kind that a full split type SSW event can produce, displacing Arctic air simultaneously across the eastern, central, and western United States, would not stress a single regional grid. It would stress multiple regional grids simultaneously. The mutual aid compacts that grid regions use to share resources during emergencies depend on neighboring regions having resources to share. In a simultaneous multi-region event, the compacts cannot function as designed. FEMA's compound event section, 2 pages in a 512-page document, does not provide the operational specificity needed to coordinate a multi-region simultaneous grid, gas, and water failure. The January 2024 SSW event was the strongest in the satellite era. Arctic amplification means the temperature gradient that historically limited the equatorward displacement of polar air is reduced. The compound failure cascade that this investigation has described in detail is not a once-in-a-century tail risk. It is a once-in-a-decade scenario that the preparedness posture of the infrastructure it will encounter has not fundamentally improved since February 2021. These three interpretations share a common data foundation. The difference between them is not in the facts, the compliance percentages, the operating reserves, the SSW frequency, the Arctic amplification rate, but in how those facts are weighted against each other and projected forward. The benign interpretation weights the system's demonstrated resilience. The intermediate interpretation weights the measured gaps. The concerning interpretation weights the compound mechanism and the simultaneous multi-region exposure that NERC has documented. Only the next event will determine which interpretation was right, but the data does not support the conclusion that the situation is under control. It supports the conclusion that the situation is being managed with decreasing margin under forcing conditions that are increasing. What data would distinguish between these interpretations? The post-Heather PUCT audit covering the Q1 2024 compliance cycle, the full ERCOT operational dataset from the Heather event, including the frequency nadir and the unit-by-unit generation loss breakdown, the NERC Summer 2024 Reliability Assessments Winter Risk Update. These are not theoretical future datasets. They exist. Some are scheduled for public release. Some have been requested through public records channels. What they contain will either narrow or widen the gap between the interpretations. We are watching for them. The investigation closes with a ledger, not a verdict. A ledger, a precise accounting of what the evidence confirms, what it suggests but doesn't confirm, what remains genuinely uncertain, and what is unknown because the data has not been released. These are different categories, and conflating them is how investigations lose their credibility. What the evidence confirms. Sudden stratospheric warming events cause polar vortex disruption that reaches the surface within 7 to 21 days. The mechanism is established in the peer-reviewed literature and confirmed by the observational record across multiple events. The January 2024 SSW event was classified as a split type, the higher surface impact category, with a stratospheric temperature anomaly of plus 63 degrees Celsius and a zonal mean wind reversal of 50 meters per second in 72 hours. The compound failure cascade, gas supply, grid generation, municipal water, operated during Winter Storm Uri in February of 2021. The cascade mechanism is fully documented in the post-event literature. It is not a theoretical scenario. The PUCT December 2023 audit found 38% full compliance with the 46 weatherization measures mandated after Uri. Instrument winterization compliance, 31%. Heat tracing compliance, 29%. Financial penalties assessed, 0. NERC's November 2023. Winter reliability assessment flagged ERCOT, MISO, and SPP as elevated or high risk for generation adequacy under extreme cold conditions. Winter Storm Heather resulted in 6,200 megawatts of forced generation outages and an operating reserve of 3%, 5 times below the NERC recommended minimum of 15%. Arctic amplification is occurring at 4 times the global mean warming rate. The IPCC 6th Assessment Report attributes this to anthropogenic greenhouse gas forcing with high confidence, what the evidence suggests but does not confirm. The frequency of major split-type SSW events may be increasing under Arctic amplification conditions. The observational record shows 3 split-type major SSW events in 6 years versus a historical mean of approximately 1 every 3 to 4 years. This is suggestive, but statistically inconclusive. The satellite-era sample size is insufficient to distinguish a genuine trend from natural variability in a system with significant internal variance. The 62% weatherization non-compliance figure likely understates the actual operational exposure, because the measures with the lowest compliance rates, instrument winterization and heat tracing, are the measures with the most consequential failure modes. But the audit does not rank facilities by their contribution to total ERCOT generation capacity, so it is not possible from the public record to determine whether the non-compliant facilities represent a disproportionate share of vulnerable generation. What remains genuinely uncertain: the precise relationship between Arctic amplification and the frequency and intensity of SSW events. This is an active research area with genuine scientific disagreement. Dr. Jennifer Francis's work suggests the linkage is real and intensifying. Other researchers, including some at NOAA, have found the observational evidence less conclusive. The investigation does not resolve this disagreement. It names it as the most important open scientific question for this topic: what is unknown, because the data has not been released. The POCT compliance audit covering the Q1 2024 period, the audit that would show compliance progress in the 2 months following Winter Storm Heather, has not been publicly released as of the time of this investigation. ERCOT's detailed operational data from the Heather event, including the unit-by-unit breakdown of forced generation outages and the system frequency nadir, is classified as critical energy infrastructure information under NRC CIP standards. This classification is legitimate under the regulatory framework. The consequence, that the public and the policymakers and the researchers who study these events cannot independently verify the system's behavior during the critical hours of Heather, is a genuine limitation on the completeness of the picture. The investigation sent a public records request for available Heather operational data to ERCOT's public communications team. No response was received as of the time of this publication. The ledger is complete, the confirmed items are substantial, the uncertainties are named, the unknown data is identified, its location is known, and its release would materially advance the investigation. We will be here when it is released. There is a version of this investigation that ends with a warning, a final urgent appeal, a call to action framed as a countdown. That version is easier to write. It is also less honest. The evidence does not support certainty about when the next compound event will arrive, how severe it will be, or whether the preparedness gap will be closed in time to change the outcome. The evidence supports a clear understanding of the mechanism, a documented record of a prior cascade, a measured account of the preparedness gap, and a named list of the data that would allow a more complete assessment. That is what this investigation has provided. It is enough. What comes next, in terms of the investigation, not the weather, has a specific shape. The PUCT Q1 2024 audit is scheduled for release. When it is, this channel will cover it. The NERC Summer 2024 Reliability Assessment, which will include an updated winter outlook, will be published. When it is, this channel will cover it. Congressional testimony on grid winterization, compliance, and enforcement, scheduled before the Senate Energy Committee in the coming months, will provide a public record of what the grid operators and regulators are saying under oath about the state of the system. When it is available, this channel will be there. And if the atmosphere provides another test, if the MERA-2 data shows another stratospheric anomaly forming, another wave flux pulse driving toward the critical threshold, another split event developing in real time, this channel will cover it from the moment the data is visible, at the 14-day lead time that the science makes possible, not the 4-day lead time that the institutional pipeline currently provides. There are people in this community who work in grid operations, who work in pipeline maintenance and wellhead engineering, who work in municipal water systems and emergency management, who have direct access to operational data that the public record does not contain. If you have seen something in these systems that the data in this investigation describes, if you have watched a compliance audit process from the inside or managed a generation unit through a cold weather event with equipment that wasn't finished, or worked a water main repair crew during a simultaneous multi-break event, the comment section is a place to say so. The investigation is richer for what the community brings to it. This is what Signal Watch does. Not warnings, not predictions. Evidence, mechanism, historical record, preparedness assessment, and the commitment to be here when the next data point arrives, whether it comes from a government audit, a satellite reanalysis, or the atmosphere itself delivering another test of a system that the record shows is managing its margin carefully. We will be watching, and we will be here when it matters.